favors the reaction. In this case, a spontaneous reaction is dependent upon the temperature, modification of the temperature, and the change in entropy term being small relative to the change in enthalpy, so that this free energy is negative. So the freezing of water is an example of this type of process. So it is spontaneous only at a temperature above 273. So if it is spontaneous only at a relative low temperature above 273 Kelvin, so if the temperature is below 273 Kelvin, then it will not melt, because at that point the enthalpy is high. So the larger delta S value causes the sign of delta G to be positive, and freezing does not occur. Let's take note of that. Okay, we have change of state and free energy. Now, at the temperature at which a change of state occurs, the two states are in equilibrium with one another. For an ice water system, equilibrium takes place at 0 degrees Celsius. So delta G is equal to 0 at that temperature. So the heat of fusion of water is known to be equal to 6.01 kJ per mole. And so the Gibbs free energy equation can be solved for the entropy change that occurs during the melting of ice. The symbol delta S fus represents the entropy change during the melting process, while TF is the freezing point of water. So take note of this formula, where you can have delta S fusion, that is where you have to get delta S here, you use your change in enthalpy over the temperature given. So you must take note, because at times you need to know different ways, different formula that you can use to find your change in entropy. So here is one of the formula. You can also find entropy, change in entropy, using the previous formula, that is your change in Gibbs free energy delta G equals delta H minus T delta S. So you can find delta S there. Just make delta S subject of the formula. That's one. Then this is another one here, where you have your delta S to be equals to delta H over T. The entropy change is positive as the solid state changes into the liquid state. If the transition went from the liquid to the solid state, the numerical value for delta S will be the same, but the sign will be reversed, since we are going from a less ordered to a more ordered reaction. So if by the time you are moving from a less ordered reaction to a more ordered reaction, then you should know that your entropy will be decreasing. So a similar calculation can be performed for vaporization too, just as we have in the other one in freezing. So we can also have it here under vaporization. Still that formula, the heat of vaporization over temperature will still give you the change in entropy. So okay, let's look at this paragraph. From this calculation, we can see that our answer here shows that the entropy is positive. We said the value is positive, again reflecting that increase in disorder going from liquid to vapor. Condensation from vapor to liquid could give a negative value for delta S. So if you are going from a liquid to vapor, there will be increase. So since we are dealing with vaporization, so you expect that your entropy will be positive, because there will be increase in disorderliness. But if it is condensation, then there will be decrease in entropy. So take note, Condensation will give you decrease in entropy, while vaporization will give you increase in entropy. Now the gives energy in reaction. We said we've talked on spontaneous reaction. Remember, we say it's a reaction that is considered to be natural. It's a reaction that is considered to be natural because it is a reaction that occurs by itself without any external action towards it. That's why I said it occurred naturally. While non-spontaneous need constant energy being applied to it in order for it to process, in order for the process to continue. And once you stop the external action, the process will cease. So for a non-spontaneous reaction, you have to induce it, you have to force it to form a product. If you stop all those external efforts, the reaction will stop. But for spontaneous reaction, there is nothing like external force. On its own, it can proceed to form a product. Take note of that difference between a spontaneous and non-spontaneous reaction. When solving for the equation, if change of G is negative, then it is spontaneous. I told you that whenever Gibbs free energy is negative, it is spontaneous. If Gibbs energy is positive, then it is non-spontaneous. The symbol that is commonly used for Gibbs free energy is G, and it can be more properly considered as standard free energy change. That's delta G. In chemical reaction involving the change in thermodynamic quantity, a variation on this equation is often encountered. So here we have the formula for calculating Gibbs free energy. I told you earlier, we have delta G equals delta H minus the product of temperature and change in entropy. So take note of this formula for calculating Gibbs free energy. So from this formula, you should know you can use it to calculate change in entropy, you can use it to find temperature, you can use it to find change in entropy. It's just a matter of change of subject or formula. Now let's look at this example. Calculate the change in Gibbs free energy at 290 Kelvin for the following reaction. Now this is the reaction leading to the formation of nitrogen 4 oxide. So we have this. Now given that your enthalpy change is minus 120 and then your entropy change is also minus 150. So just put this value, go back to the formula, delta G equals to delta H minus T delta S. So you put on this value, you will be given temperature in Kelvin, so no need for conversion again. And then, but look at our entropy. Remember, I said you must change the entropy from joule per Kelvin to kilojoule per Kelvin, since we have enthalpy in kilojoule. Remember I said that earlier. So in this case, before we can use the value of entropy here, then we have to change it from joule to kilojoule. So that is the first thing here. You can see here I have to divide my 150 by 1000 so that I will change it from joule to kilojoule. So it's now from minus 150, it's now minus 0.15 kilojoule per Kelvin. So I can now slot in the value into the formula of Gibbs free energy, and then that gives make our Gibbs free energy to be negative, minus 77 kilojoule. Okay, that is one example there. Study the example, is very simple. So since the changes of entropy of chemical reaction are not measured readily, thus entropy is not typically used as a criterion. To obviate this difficulty, we can use G. So delta G is the major things that can actually tell us if a reaction is spontaneous or not. The sign of change in delta G Sign of change in this free energy, which is delta G,